So long division is nice. Not nice, but effective. And not very pretty. Where something you're going to learn, even though you might not believe it right now, is that the more math you do, the more you'll see mathematicians like to avoid doing work. They always try to find the shortest way to get somewhere. They always try to find the easiest way to do something. That's the way math is. We like finding shortcuts where we have them. And in particular, when dealing with long division, it's clunky. So, in the mid-1600s, a mathematician by the name of Johannes Hud from the Netherlands came up with a method that would become known as synthetic division. But he had this idea that he wrote up in a letter, and he would have had probably a pretty good mathematical career if he had wanted one. He was actually very influential on Leibniz and Newton, which is to say he was very influential on calculus, but he was also the mayor of Amsterdam. And at that time, he kind of had better things to do than worry about chasing divisions around. So he was a little bit occupied, and it wouldn't be until about 1804 that Ruffini would formally put together his ideas into a thing that we call synthetic division, where synthetic division, as we present it as it's most often seen, is especially for cases that you divide a polynomial by a linear term, something in form x minus c or x plus c, but we like to standardize a little bit. And the way that this works can actually be extended. You don't need to just have it be for linear terms. It's just that it's how we see it the most, where what we do follows a pattern. That if we have some polynomial p of x and it's divided by a quotient x minus c, we arrange the polynomials in order of descending powers with a zero coefficient for any missing terms, so we carry extra zeros like I did in the last example. Then we write the coefficients of the dividend in the top row, where c is used to represent the divisor x minus c, and we put that in the next row down to their left. Then write the leading coefficient of the dividend on the third row in the same column. That is the same column as the leading coefficient of the dividend as well. That's right, it's a divisor dividend quotient. I get these words mixed up in my head sometimes. I'm going to try and be careful. Then we multiply c times the first value written in that bottom row. That is c times that leading coefficient, and put that product in the next column in the second row, where you add the values in the column and put them in the bottom row. Then you repeat this until all of the columns are filled, and use the numbers in that last row to write the quotient, where you're including the remainder above the divisor. The degree of the first term of the quotient is 1 less than the degree of the first term of the dividend as we start, and the final value in the row is the value corresponding to the remainder. So again, we can extend this, but the way that we do it algorithmically, it doesn't quite make sense as nicely if we use anything other than linear terms. It doesn't have to be linear, but it makes our lives easier, and it also just doesn't look very easy right now. Obviously, this is very complicated looking. It's a lot of steps. So let's get an example with something familiar where we can understand how these steps come together. So for this example, we want to use synthetic division to divide x cubed plus x squared minus 1 by x minus 1. So we're starting here with a division that we've already seen when we did in that last example. So we're going to see how this works in the context of something where we know how it's supposed to go. And we're going to start here by taking our dividend there and expressing it as x cubed plus x squared plus 0x minus 1. Like I said, we're going to carry in that extra 0. In this case, we actually need it to make sure everything comes in the right way. And then we are going to go into that second step. We're going to write the coefficients of the dividend in the top row. That is, we're going to take these and turn them into something a little bit more tabular. We're going to have 1 for the x cubed, 1 for the x squared, 0 for the x, and minus 1 for the minus 1. And then next to that, we're going to make another row, and we're going to put in a c for the value x minus c. In this case, c is equal to 1. It's in that nice standardized form. So we're going to put this over here. I'm going to write in a 1, and then I'm going to sort of bar this off so we have it a little bit more organized in terms of how the pieces come together. And then from there, For step 3, we write the leading coefficient in the bottom, the third row in the same column. So that means we take this guy and we just pull it down to here. And that is essentially our setup, where once we have all of this set up together, then we can start with the steps. So the actual work here means taking this, multiply it by that. So 1 times 1 will get you a value of 1, and we put that 1 over there. As it says, we put the product in the next column in the second row. So that's this location. And then we add the values in the column and put the sum in the bottom row. 1 plus 1 is 2. And once we have that 2, we're going to just repeat this. So it's just the same process a couple more times, sort of hopscotching along, where this idea of like turning our pieces into their coefficients in a nice little table where we have a fixed algorithmic process is the sort of thing you'll see a lot in linear algebra. This is not linear algebra, to be fair, but that idea of talking in terms of coefficients and shunting the variables off to the side is similar. Anyway, here we've got that 2, and the 2 is going to get kicked up to here. Then we take 0 plus 2 is 2 again. 1 times 2 will give us yet another 2, and 2 times minus 1 is 1. Where essentially what we've done here is identify the pieces from our long division. That is, identify the pieces we got out of it, where this is something like our x squareds. This is like what happened with that 2x. That's like 2, and this is our remainder. And that's exactly what we're doing. We're taking all of the parts away from it. We're taking away all of the x's and just focusing on the coefficients that are attached to them. So we end up with just coefficients, and we turn those coefficients back around. Where, to finish this off, we use the numbers in the last row, these coefficients, where we're starting with 1 less because we divided out a 1 from those things there. We divide out a 1 from a 3, and we will get an x squared plus 2x plus 2 plus 1 over x minus 1, just like we should have expected. And that's one way this can go. So let's get one more example here to understand how this is coming, where I'm not going to write out the steps along with there on that little ticker. We're just going to go through it.